more of an introduction for the homework than actually something new. So we're going to talk about something called Heisenberg model, which is something that you kind of know, you'll see. And then you're going to talk a bit about, so you talked in the video about Monte Carlo simulation for Heisenberg model. So the homework exercise you're going to do a simulation, to write a simulation. So I'm going to talk a bit about that. I also gave a bit more time for that homework because usually it just takes more time. So instead of all of the students, instead of people asking for extensions, we just start with. So I gave a bit I think 2 weeks. Also, the homework going to be a bit more less frequent from now on. So we can do that. I also saw people complain about that in the teaching survey. So yeah, so that's going to be. Okay, so I'm going to start with super quick reminder of spin. For those of you who did quantum mechanics too long ago or something, so in general, we have the spin operator, consists of it has 3 ingredients, Sx, y, z. We have the commutation relations between the different components, so for 2 components, x, y, or z, commutation relation would be I, h bar, epsilon, I, j, k, and then s, k, where this is the Levi-Civita operator. So if I, j are cyclic, this is equal to 1, minus 1 if they are anticyclic, and 0 elsewhere. So x, y, z will give you 1. If you go the other way around, to give you minus, and if you have x and x or y and y, it's going to give you 0. What else? Yeah, so the operators themselves, the eigenstates. We have 2 operators that we usually look at. So s square. So that's going to be sx squared plus sy squared plus sz squared. So the eigenstates are consist of 2 quantum numbers. So s is like the quantum number of s squared, and ms is going to be the quantum number of the projection on the z direction. So if so s squared acts on that state, going to give me h bar square s plus 1, and sz going to give me h bar m s m. Just going to do m instead of ms. Okay. So addition of angular momentum. Momenta in plural. So if you have so we have some, we can call it like J or S. Let's stay with S because we have S later. So we have S of, so we can have either, we can have 2 particles, each one with different spin. We can have 1 particle, and we're going to look at like the angular, the spin and the spatial, and the orbital angular momentum. So this is if we look at like specifically two different components, S1 and S2. the quantum numbers of the new operators going to be, so S, which is like S total, going to be between S1 plus S2 to S1 minus S2. And M going to be M1 plus M2. So, for example, if S1 equal S2 equal half, the beloved example, then S going to be equal to either 0 or 1. And then if S equals 0, M can only be equal to 0. And if S is equal to 1, I'm going to be equal to either 0 or plus minus 1. And then we're going to have triplet and triplet, and so on. So I'm going to assume that you remember how to do addition of angular momentum from a technical point of view. In general, you can have, we have the Clebsch-Gordon coefficients. So if I want to write a new state in the base of the total angular momentum S, I have some states S and M, some specific states. I'm supposed to be able to write it as like a summation over, like a superposition of it. Summation of states in the old basis. So I'm going to have some coefficient that multiply S1, M1, S2, M2. So this is a specific state, and here I have a coefficient that depend on S1, S2, M1, M2, and the new coordinates, the new quantum numbers S and M, and I'm going to have a summation over M1 and M2. So, for example, in the case of S1 equal S2 equal half, we're going to get, so one specific state would be, so S equals 0 and M equals 0. So the Clebsch-Gordon coefficients, I'm going to have two coefficients that equal either to minus or plus 1 over square root of 2. One for the state of M1 equal half, M2 equal minus half, and I have minus for M1 equal minus half and M2 equal half. And then all the other coefficients for the specific state are going to be 0. So you know all of that. Cool. So why do we care about any of it? So this Hamiltonian, I don't know if you saw specifically the Heisenberg model. If you saw it already, so great. But if you didn't, this looks very similar to what we know usually from Ising model. You remember? So vector. So in the case of the Ising model, we have the same Hamiltonian, but S is not a vector. It can only get values of plus and minus 1. And so this is like a classical interpretation, kind of one-dimensional classical interpretation of that model. And we're going to talk more about that actually in the following tutorials. But this is basically like the quantum three-dimensional version of that. So this is basically just specific Hamiltonian of something that you already know how to solve, because you already know how to solve that type of stuff. So this is just, you know, a specific version of that. So for any given Hamiltonian of that form, you know, you can solve it as you usually solve problems in quantum mechanics. So you see that everything here is a vector. So Si and Sj are the spin vectors we mentioned in the beginning. The magnetic field is also a vector, and I and j are any they represent the interaction of the nearest neighbors coupling. So this is like nearest neighbors, or it can depend on the model, but it's usually nearest neighbors. So this is the Hamiltonian. So in general, we can have two options for the type of interaction. So if J is a positive, it's a positive number, so we have a positive coupling. It means that we have a ferromagnet. This is like the classical model. So that means that we want to minimize the energy, because we have a minus, we want all of the spins to align in the same direction, which makes sense. But if J is smaller than 0, so I have negative coefficient, so this is overall going to give me something positive, and then this is antiferromagnet, which means that the spin's going to want to go in the direction that's opposite to the neighbors. So if we look at like two-spin system, so if the first one will be up, the other one will be down. If we have one-dimensional system, this is also very easy to imagine. They're just going to go to tectons. But if we have some like a different geometry, the solution of the antiferromagnet is going to be sometimes very non-trivial, as we're going to see. So let's look at some specific system. So in the homework, so I'm going to solve. So in the homework, we're going to have a question about the Heisenberg model, and the first part of the question is going to be what I'm going to solve now. So you already have part of the homework ready. So fine. So we have a triangle. And in each point in the triangle edges, we have a spin. So let's say this is S1 and S2, S3. And between each two spins, we have some coupling coefficients. So here we have J, and J, and K. Let's call it minus because I want to be consistent with what we do later. So the Hamiltonian of that system, and I don't have any magnetic field. So the Hamiltonian of that system is going to be, so I have K multiplied by S1, S2, plus J, S1, S3, plus J, S3, S2. So,
this is part of a lattice?
What?
This is part of a larger lattice?
For now, no. For now, this is like a...
How can it be like two coefficients that are the same and then the third one not.
Why not?
How does it keep symmetry in the lattice?
You have symmetry between that interaction and if you change.
Yeah, but when you let's put two.
You can put like more triangles here and you can keep the lattice, which is actually what we're going to do in the homework. But you can solve like series this time like. So K and J can be either positive or negative. I write them in that form again for consistency. What I'm going to do later, but I didn't say anything yet about the sign. Okay, so what I want to do is what I usually want to do in quantum mechanics actually, which finds the eigenstates and the eigenenergies of the Hamiltonians. So we want to find eigenenergies. So there are a few ways to solve that. So I'm going to solve it in one. I'm going to solve it in one way. There's another way that you can use like raising and lowering operators and write it in a form of a matrix. Also put that in the note. Instead, someone is I don't know bored because you get like 8x8 matrix, but you know. So that's another option. So I'm going to solve it with addition of angular momentum. So this is actually completely identical question to something that you solve in quantum mechanics too. So it should be easy. And then we're going to see when we get the result, we're going to see why is that actually interesting. So let's define two new operators. One is S1 new, 1, 2, which is S1 plus S2. And one is S1, 2, 3, which is S1, 2 plus S3. So using those two, so this Hamiltonian is clearly very, like, we cannot really solve it in its current form because all of those are vectors, so this is not very convenient to work with, so we want to write it in a form of operators that we know how to diagonalize. So if I define, for example, S12 in that way, then S12 square is S1 square plus S2 square plus 2S1, S2. And therefore, I can write S1, S2 as half S1, 2 square minus S1 square minus S2 square. So all of those are operators that I know how to diagonalize. So this is much better to work with. And in the same way, I can rewrite S13 plus S23 with the second operator that we defined, with so S123 square is equal to S12 square plus S3 square plus 2. So we have S3 multiplied by S12, so this is S1, S3 plus S2, S3. And then we can do the same as we did here. So overall, we can rewrite the Hamiltonian as K over 2 S12 square 2 square plus J over 2 S123 square minus S12 square minus S3 square. we need to do is to find the values of the to add the angular momentum to find the values of the new quantum numbers. So the way that we do that, we don't even actually have to calculate the actual eigenstate. So if we start with S1, so all of those spins, I didn't say that, but all of those spins are spin half. So all of those equal to half. Then I have two options for S12, either equal to 0 or to 1. And then if I add also S3, so this is S1, 2, 3, can only be equal to half, because half and yeah. But if S12 equal to 1, so S3 I either add the half and then S1 to 3 equal to 3 over 2. Or I subtract the half and then just get half. So we have overall 3 possible states, which means we're going to have 3 different energy levels. So let's calculate those. Okay, so for S12 equals 0 and S123 equal, so S12 equal, yeah, okay, S equal to 1 and this is 3 over 2. So, so the energy is equal to h square k over 2. So we have, you remember the eigenstates are s plus multiplied by s plus 1. So for S12, I'm going to have 2 minus. So I have for S1 square, I have half multiplied by 3 over 2, so overall 3 over 4, minus 3 over 4, plus j h bar square over 2. So 3 over 2 multiplied by 5 over 2. Minus 2 minus 3 over 4. So, so overall we get 3 over 2. So 2 minus, no, I'm just going to copy the answers. So k over 4 plus j over 2 for so for S12 equal 1 and for S123 equal half. The energy calculated in the same way, maybe. So we have k over 4 minus j, and for S12 equals 0, the energy is minus 3/4. Okay, so we got two energy levels, three energy levels. So let's look about the triangle that we started from. So let's assume for a second that J is equal to K, just for convenience, and then we can like generalize it. So we have J. So if J is positive, and you remember that it's a Hamiltonian with plus, so that means it's an antiferromagnet. So how are the spins going to behave? So let's say this spin is going to be up, then that spin is going to go in the other direction than that spin because it's an antiferromagnet. So this is going to be down. Now S3, you have a problem because you want to go up because of that, you're going to want to go down because of that. So it's actually going to happen that it can go either way, because in a quantum system it's going to be in like some form of entangled state. So we have like a superposition of states. We'll not go too deep about how it's actually going to look, but you understand it's going to be a superposition of either down or up. And so if we look at the energy levels that we calculated, we see that in the case J equal to K, the energy gets only two different values, either plus or minus 3/4 K H plus square. So this is going to be so the minus sign is going to be for that, and plus for that. So the system wants to go to the lowest energy level, which is the minus in that case, and we have two possible states for that. And in both cases, S1 to 3 is equal to half. So if S1 to 3 equal to half, then it means that that M can go either to plus minus half. That means that two of the spins are going to be in one direction and the third spin is going to be in the other direction. Now, which is going to be in which direction, we don't know because it can go either way. But you can see from the calculation of the energy itself that we have those two options, and the case that we have plus, which is the case that the system doesn't want to go to because it's higher energy level. It's the case where all of the spins going to align in the same direction. And you can also see that if I change the sign, if I change the sign of J, so I get ferromagnet instead of antiferromagnet, the system going to want to go to that state where all of the spins align in the same direction. So that's going to be the new ground states, which make sense. So that thing called it's called fast-weighted system, and it can happen in either in a case usually where you have an antiferromagnet, or if you have a mixed coupling. So if I have in some of those, I have in some of those cases like a positive coupling constant, and in one I have like a negative coupling constant. So you're going to have competing behaviors between the different spins. In the case of ferromagnet, of course, I cannot have that because all of the spins just going to align in the same direction. If the geometry of that system is going to be more complicated, it's going to be very hard to calculate. And if I take some different values, so if I have here K that have different value than J, so I'm still going to have some kind of a fast-weighted system. It's just going to have some phase, it's not going to be either up or down. It's going to be some phase between the different between the different states. So this is just, in a very general way. So this is why this system is basically interesting to begin with. Now, in the homework, what you're going to have is like a chain. So we have like something like that. So, it starts, so you have n triangles and they go like in a line. And you need to use a like variation method to calculate the energy. So if you remember, you need to basically you're supposed to guess like a wave function. So in the question, the wave function is given to you, so you're not supposed to guess that. And then you need to work under the assumption that any energy that you're going to calculate is going to be larger than the actual ground state of the system. So you're going to get some energy, this is approximated energy, and this is the assumption that you're going to follow to prove what you're asked to prove in the question. So this is basically, what the question is about. Did I have anything else? Okay. Okay, so do you have any questions about that before I go to talk about Monte Carlo? Cool. Okay, this is going to be a very short tutorial. Okay, so as I said, you're going to have a homework exercise that you need to write a code that follows Monte Carlo algorithm, and then you're supposed to get eventually, I think, like the average magnetization, susceptibility, heat capacity, and energy. So we have formulas for that in the exercise too. So there are just a few points that I wanted to say in class, because those are stuff that usually people have problems with. So the algorithm itself is also given in the exercise. Like you have the algorithm, you just need to write the code that follows the algorithm. And you also talked about that with Vido. But if you have because it's a coding problem, and this is just not a coding course, so if you get the results for any of those stuff or any of the other stuff that the question asks you to do, and you get something that looks like just doesn't make sense, like the magnetization is always 0 or something, or so I don't mind too much about the code. So if you get something that looked to you weird, so I just wanted to explain why it's weird, and why it is weird, and what do you expect to get. So it doesn't mean that you can just like submit like random code, but just make sure that you know what you're supposed to have, more or less, especially for stuff like magnetization and energy. So in the beginning of the homework, you need to do you ask to get snapshots of the system. So the question is like that: you have two-dimensional grid. So you have something like that, and each point is like spin, and it's either up or down. and you start from some initial condition, and then you ask to give like snapshot of the system for different times. So this is something that's like, if your code doesn't work, like the algorithm itself doesn't work, you're going to see it here, because you start from something that's random, and if you're in low enough temperature, this is going to be like ordered eventually. So first of all, it's to give you a perspective of which temperatures you need to work in. But I think in that specific case, you're given like the specific temperature that you need to use. And if you have a problem calculating like those, you're afraid that you have a mistake here. Here you're going to see it here. Like this is what tells you if the code is wrong, or if the calculation is the part that's wrong. And the second part, that's like self-check question, is to calculate the magnetization for specific temperature. So it's like magnetization, average magnetization versus kind of time, but it's actually a number of iterations, it's not really time. And what happened here is that you start from this disordered system, so you're going to start somewhere around here, and when you continue to go to do more and more iterations, you have something with noise, and then eventually you expect to get something that like a plateau in the system when you get to equilibrium. So the point of that part is to tell you how many iterations you need to take in order to get to equilibrium, because many times students ask how do you know how many iterations to take. So that's why that part exists. What else? Yeah, magnetization, like this may be like trivial or not, but when you calculate average magnetization, so you sum over the states of all of the spins, so you have some MI. So you take the absolute value, otherwise you get 0. So some of them. So what? Sorry, no. I wanted not the magnetization. Okay, forget about it. I wanted to say something else. Okay, let's stay with that. Okay, yeah, I think that's basically it. So you're going to get some behaviors of those different variables. We're going to talk more about all of that like phase transition topic like later in the course. So this is going to be like an intuitive introduction. Yeah, and I think that's basically it.
Thanks.
שאלה לגבי המטלה שיש להגיש מוכן. הייתי במילואים ביום רביעי חמישי, שרוצה לקבל